Refrigeration cycles. This chapter discusses refrigeration cycles as the reverse of power cycles, where the main objective is to transfer heat from a low-temperature region to a high-temperature region with the help of work. This system is the foundation of refrigerators, air conditioners, heat pumps, and industrial cooling systems. The main goal is not to produce work, but to produce a cooling effect. These concepts are essential in modern thermal engineering and energy systems. The discussion is based on energy balances and the second law of thermodynamics.
Lesson Plan: Position of refrigeration cycles. Refrigeration cycles are placed after gas power cycles and vapor power cycles because conceptually they are their reverse. Students are expected to already understand Carnot, Rankine, and Brayton cycles before entering this topic. With this sequence, the comparison between power cycles and refrigeration cycles becomes clearer. This topic also serves as a bridge to gas mixtures and air conditioning. The structure is arranged to build understanding step by step.
Learning outcomes. The learning outcomes emphasize understanding the concepts of refrigerators and heat pumps and their performance measures. Students are also expected to analyze ideal and actual vapor compression cycles. In addition, the second law is used to evaluate real system irreversibilities. Refrigerant selection is also an important aspect related to environmental impact. By the end of the chapter, students should understand various modern refrigeration systems. Refrigerator versus heat pump. A refrigerator is defined as a device that removes heat, QL, from a low-temperature space and rejects it to a warmer environment. A heat pump uses the same principle but focuses on the heat, QH, delivered to the warm space. Both require work input, WN, to operate. From an energy perspective, the systems are identical. The only difference is the definition of the desired effect. Carnot refrigerator cycle consists of a compressor, condenser, turbine, and evaporator. On the TS diagram, heat absorption and rejection occur at constant temperatures. This cycle is completely reversible and has no irreversibilities. Therefore, its efficiency is the highest theoretically possible. In practice, this cycle is very difficult to implement. The Carnot refrigerator cycle transfers heat from a cold area, QL, to a warm area, QH, using a compressor, condenser, turbine, and evaporator. Vapor compression cycle components and TS diagram. The vapor compression cycle consists of four main components: compressor, condenser, expansion valve, evaporator. The compressor requires work input, WN, to raise the pressure and temperature of the refrigerant. In the evaporator, heat, QL, is absorbed from the cold space, while in the condenser, heat, QH, is rejected to the surroundings. The TS diagram helps visualize phase change and thermodynamic property variations during the cycle. This cycle is the backbone of almost all modern cooling systems. Refrigerator cooling mechanism and heat transfer process. The cooling mechanism of a household refrigerator is based on heat absorption in the evaporator and heat rejection in the condenser. Heat QL is removed from the freezer and refrigerator compartments to keep them cold. This heat is then transferred and rejected as QH to the kitchen air through the condenser. The capillary tube controls the refrigerant flow to create the required pressure difference for expansion. This entire process runs continuously as long as the compressor operates. Answer C. Release absorbed heat into the kitchen air. Ideal vapor compression cycle and pH diagram. The pH diagram is used to visualize pressure and enthalpy changes during an ideal vapor compression cycle. The four main processes are compression, condensation, expansion, and evaporation. Heat QL is absorbed in the evaporator, and heat QH is rejected in the condenser, while work WN is supplied to the compressor. This diagram is very useful for numerical performance calculations. With this diagram, the cycle efficiency can be analyzed quantitatively. Actual vapor compression cycle inefficiencies. The actual vapor compression cycle always contains irreversibilities that cannot be avoided in practice. Heat is still absorbed as QL and rejected as QH, but with higher work input. Non-ideal compression, throttling expansion, and pressure losses degrade performance. The TS diagram helps identify where these losses occur. This analysis is important to find opportunities for efficiency improvement. ODP, GWP, and safer alternatives. This slide emphasizes the difference between harmful refrigerants and more environmentally friendly ones. Refrigerants such as R11, R12, and R22 have very large environmental impacts. In contrast, ammonia and some newer HFCs have zero ODP and lower GWP. However, every refrigerant still involves trade-offs between safety, performance, and cost. Therefore, refrigerant selection is always a complex engineering decision. Ammonia and newer HFCs like R32 are considered environmentally friendly refrigerants because they have zero ozone depletion potential, ODP, and lower global warming potential, GWP. Second law analysis in vapor compression cycle. Second law analysis is used to evaluate how far the system deviates from ideal behavior. Each component, such as the compressor, condenser, expansion valve, and evaporator, generates entropy. This entropy generation is what causes the actual COP to be lower than the ideal COP. With this analysis, the main sources of losses can be identified. This approach is very important for designing more efficient systems. Heat pump dual functionality and seasonal operation. A heat pump operates on the same principle all year, but the direction of refrigerant flow can be reversed. In winter, the system extracts heat from outside and delivers it indoors for heating. In summer, it works like an air conditioner by rejecting heat from indoors to the outside. The reversing valve allows the condenser and evaporator to swap functions. With one system, both heating and cooling demands can be met efficiently. Cascade refrigeration system. A cascade system uses two stages of refrigeration cycles to achieve very low temperatures. The heat exchanger between the two stages acts as a condenser for the lower stage and an evaporator for the upper stage. With this arrangement, the total compressor work can be reduced. The TS diagram shows that each stage operates over a narrower temperature range. This concept is widely used in cryogenic and very low temperature applications. Answer B. Act as a condenser for the lower stage and an evaporator for the upper stage. Two-stage cooling system with flash chamber. This system uses a flash chamber to separate liquid and vapor after the first expansion process. The vapor goes directly to the high-pressure compressor, while the liquid undergoes further expansion before entering the evaporator. With two compressors operating at different pressure levels, the total work can be reduced. The TS diagram shows a staged cooling process that is closer to ideal behavior. This system is suitable for low-temperature applications. Single compressor system explanation. The main concept of this system is efficiency and simplicity, while still serving two temperature levels. A single compressor raises the pressure of the entire refrigerant flow before it is split into two paths. Each path then absorbs heat from a different compartment. After that, the flows are combined again before entering the compressor. With this design, system cost and complexity can be reduced. Lindy-Hampson process explanation.
The Lindy-Hampson process relies on cooling effects from expansion and regenerative heat exchange. A regenerator is used to recover cold from the outgoing stream. In this way, the efficiency of the liquefaction process can be improved. Cooling occurs gradually until part of the gas becomes liquid. This process forms the basis of many modern cryogenic systems.
Hydrogen liquefaction with pre-cooling and throttling. In this system, hydrogen is first cooled through several pre-cooling stages. Nitrogen is used to help reach very low temperatures before the final process. A throttling valve is then used to reduce the pressure and produce some liquid hydrogen. Each stage aims to reduce the cooling load of the next stage. This is a real example of refrigeration applications in hydrogen energy technology. Gas refrigeration cycle components and cooling mechanism. The main components of this system are a compressor, a turbine, and two heat exchangers. The compressor raises the pressure and temperature of the gas before it is cooled in the first heat exchanger. The gas is then expanded in the turbine to produce a significant temperature drop. After absorbing heat from the cold space, the gas returns to the compressor and the cycle repeats. Although simple, this system has a relatively low COP compared to vapor compression systems. Answer C. Expand the gas to reduce its temperature for cooling. Gas refrigeration versus reversed Carnot cycle. This diagram compares the performance of the gas refrigeration cycle with the reversed Carnot cycle. It shows that the Carnot cycle provides a larger refrigeration effect for the same work input. The gas cycle requires more work to achieve the same cooling. This difference is due to irreversibilities and the single-phase nature of the process. This comparison confirms that the Carnot cycle represents the theoretical upper limit. Air cooling process in aircraft. This system is used in aircraft to provide cool air for the cabin. Outside air is compressed, so its temperature increases. Then it is cooled in a heat exchanger. After that, the air is expanded in a turbine, so its temperature drops significantly. The cold air produced by the expansion is then supplied to the aircraft cabin. This system is chosen because it is simple, lightweight, and reliable. Air refrigeration cycle explanation. In this cycle, air passes through several stages of heat exchange before and after expansion. The regeneration process helps recover energy that would otherwise be wasted. After expansion in the turbine, the air reaches a low temperature that can be used for cooling. The air then returns and completes one cycle. This approach improves efficiency compared to the simple gas cycle. Solar-powered absorption refrigeration cycle. In this system, solar energy is used as the main heat source to drive the cycle. The generator heats the solution so that ammonia is separated and flows to the condenser. After passing through the evaporator and producing a cooling effect, the ammonia is absorbed back into the water. This cycle requires very little mechanical work. This is the main advantage of absorption systems for waste heat or solar-based applications. Energy flow and maximum COP in absorption system. An absorption system can be analyzed as a combination of a reversible heat engine and a reversible refrigerator. Heat Qgen is used to produce equivalent work that then drives the cooling process. The maximum COP of this system depends on the temperatures of the heat source, the environment, and the refrigerated space. Theoretically, the COP can be derived from the temperature relations Ts, T0, and TL. This analysis shows that the performance of absorption systems strongly depends on the quality of the heat source. Answer C. The temperatures of the source, T sub S, environment, T sub 0, and refrigerated space, T sub L. References. This slide states that all figures and most of the concepts in this chapter are taken from the book Thermodynamics, an Engineering Approach by Çengel, Bowles, and Kanoglu.
This book is an international standard reference in engineering thermodynamics. Using this reference ensures that the material is consistent with widely accepted theory and practice. Students are encouraged to read the relevant chapters directly for deeper understanding and problem-solving practice. With this reference, the discussion of refrigeration cycles has a strong academic foundation.